we're going to talk about the rational roots or rational zeros theorem. So in order to do this, I wanted to first review you on some vocabulary. So if you look at the vocabulary that's listed here, you'll see the first thing is your rational numbers. Now basically what a rational number is that a number that can be expressed in the form a over b, where a and b are integers. That's what that capital Z stands for. That's the set of all integers, which is your positive and negative numbers. And b cannot equal 0. And the reason b can't equal 0 is because we can't divide by 0. I can't have 5 divided by 0. That's not a proper fraction. So b cannot be 0. Basically, it's numbers that can be expressed as fractions. So, and I know you can see my screen. So if you look at the examples here, so now we're looking at the examples, you have 2/3, 1/4, -5 over 9, 2,145 over -176. There's an infinite number of fractions. But something that you need to understand too is that whole numbers, like for example 5, that is a rational number because what's another way I can write 5? 5 over 1, which follows the definition a and b, where a and b are integers and b is not 0. So any whole number can be written as a fraction and is also considered rational. Same thing, if I give you -26, that is also a rational number because -26 can be written as -26 over 1. Vocabulary at the bottom, roots, zeros, solutions, x-intercepts, for our purposes here, all mean the same thing. Those are the things where, those are the values where the graph intersects the x-axis, as you can see it right here, and where y is equal to 0, which is where we get the term zeros. It's where y equals 0, because when y equals 0, that's when we're crossing the x-axis or the x-intercept. So what I'm going to do is I'm going to give you another example here, or give you a few examples. So let's look at some examples of some zeros. Zeros are going to be present in every kind of graph that we have, any kind of polynomial function that we can put on an xy axis in a Cartesian plane. So for example, let me give you a graph here and let me make it fairly simple. So we'll make these axes simple here. That'll be -4. That'll be 4. So I'm going to give you a graph. I'm going to give you a polynomial function of some sort. So let's start off with a polynomial function that, say, looks like this. And again, these aren't going to be perfect. I'm just giving you examples. So when we look at the rational root theorem, we're looking to try to find all the possible rational roots. It's possible that functions can have irrational roots, which means that where the polynomial function or the function itself crosses the x-axis, but it's not a rational number. Let's say it crosses at pi or square root of 2. Those are numbers that we cannot write as fractions. So they're roots, but they're not rational roots. What we're focusing on with the rational root theorem is the actual rational roots. So we are wanting to know only the rational roots. Well, before we get into specifically isolating which roots are rational, which roots are not rational, let's take a look back over at this picture. So I have 3 locations that I can see here where this function crosses the x-axis. Those are my zeros, which I also call roots, x-intercepts, solutions, zeros. So zeros, solutions, roots, and x-intercepts, they all mean the same thing. So if I were to actually give the value coordinate-wise of each of these, this one is at 5, 0. And remember, for rational roots, they have to be able to be placed into fraction form. And remember, the y-intercept is 0. I mean, the x-intercept is 0, so the y-coordinate is 0, which is what we have. So this one here is 2, 0. And this one here is a -3, 0. If you notice this condition right here, what are all my y-coordinates here? They're all zeros. And those are all rational zeros because my x-coordinates are all whole numbers, which are rational numbers. So that's what we're looking for when we're following this theorem. So let me give you another example. I know I have lovely handwriting. So let's do another one. 1, 2, 3, 4, 5. Just trying to make this simple for you. Make that 4, make that -4. So I'm going to draw another function. And I'm going to have this function cross here. So let's do something like this. And again, I'm just being creative. This could be a piecewise function. There's just all kinds of things this could be. But bottom line is we're looking at where things cross the x-axis. So there's one root, there's another root, and there's another root. Now, not all these roots have to, not all of these polynomials have to have 3 roots. This just happen to be the examples I'm giving you. Now, let's say these are our roots. Let's say that that one is at -3.50. Let's say this one is at -1/3 0. And let this say this one is at pi 0. You know, pi is about 3.14. So if I want to look for roots, those are definitely all my roots. I've got 3 roots there. But the question with rational roots is which ones can be written as fractions. So let's take a look. Pi is not rational. You will never see pi written as a fraction because it is a number that cannot be put in fraction form and be exact. Can we estimate and round? Yes, we can. But with pi is a decimal that goes on infinitely and does not repeat. So I cannot write that as a fraction. So while pi is a root, it's not a rational root. So let's look at the rational root. So let's look at the next one. The next one is -1/3. So we know that pi is not rational. Is -1/3 rational? Well, it fits exactly what we talked about. Remember, we're looking for numbers in the form of a over b, right? And that's what we have with -1/3. So -1/3 would be one of those rational roots. Okay. Now, showing you that just because something is in decimal form also doesn't mean that it's irrational. Remember, pi is is a decimal that goes on infinitely and never stops. But we can't write it as a fraction. But -1/3 actually could be written like this. And what happens with those 3's? They go on forever, right? When a decimal repeats, we can write it as a fraction. So that's why -0.3333 repeating can be written as -1/3. So rational roots, for our purposes, we're going to look at them being fractions. But just because something's not written as a fraction doesn't mean it can't be written as a fraction. And the last one is -3.5. So if I have -3.5, I could also write that as -3.5. And that is also rational. So -3.5 or -3.5 and -1/3 are your 2 rational roots. Pi is a root, but it's not rational. So that's the vocabulary portion for the rational roots. Now let's actually get into looking at how we find rational roots. The rational roots theorem is very complicated, and I'm going to shorten it here and I'm going to truncate it a little bit so that it's not so long. So I want you to be able to understand it without having to read a lot of extra text. So I'm going to simplify it for you. So the rational roots, or zeros, whatever you want to call it, theorem states the following. So here's the theorem. It's a long, drawn-out theorem, but I'm going to be very simple with you. I'm going to just explain to you how you find the rational zeros. This is for polynomial functions, first of all. Now, polynomial functions, they take on the form f of x, g of x, h of x. Just your general polynomial, your quadratic, your cubic, your quartic, your, all of those functions are polynomial functions. So I'm going to give you a sample and just show you how it's set up. For any polynomial function, and we'll call the polynomial function p of x instead of f of x because it's polynomial, you're going to have a bunch of coefficients, and you're going to have a bunch of variable terms. So let's just do an example. Let's pick a polynomial function, and let's make this polynomial function 3x to the 5th minus 4x to the 4th plus x cubed minus 5x squared plus x minus 2. Now that's long. And if I asked you where does that cross the x-axis, a lot of you would graph it, but what if it's not whole numbers? You do trace, Desmos, the calculators, they always round the numbers. So here's how we find the possible rational numbers. Now remember, going back to this example here, we do have a root that's irrational, and we've got two that are actually rational. So when we do this theorem, we're only looking for the rational one. So for the previous example, pi wouldn't show up. This is going to find out all possible, and the key is all possible rational roots. It's not going to give you all the roots, but it's going to give you all possible rational roots. And apologies there that the pen's not working that great. All possible rational roots. Possible, the key word. Possible means they aren't necessarily roots. They're just possibilities. So here's what we're going to do. The first thing we're going to do is we're going to label some things. P is going to be, P is going to be your constant term. Now we know in a function, the constant term is the one without a variable attached to it. It's called constant because it never changes. So that's going to be -2 for this example. But we'll come back to that. Q is going to be your lead coefficient. We'll just do lead coefficient. In this case, it is 3. So we're going to use these two values to find all of our possible rational roots. So our rational roots are going to be in the term in the format P over Q, and I'm just trying to stay color-coded. P over Q. And what we're going to put on top is all possible factors of each one. So we are going to factor, let me put this in white. In fact, I'll move this over to keep this a little bit uniform. We'll put it over here. We'll do P over Q. So we are going to factor P and Q. Factor P and Q. So let's start. Factor. What does factor mean? Multiplication. Factor means multiply, right? So if I'm looking for factors of a number, I'm looking for things that I can multiply together to get that number. So let's look at some of these factors here. Okay. Let's start with P, our constant term. What are some factors of -2? Well, I can either do -2 times +1, right? Or what else could I do? +2 times -1. Are there any other possible factors? They aren't. There aren't. The only factors of 2 are 1 and 2, and since it's -2, that means every pair has to have a positive and a negative. So here's how we're going to write it. we're going to write it to simplify it as plus or minus 1, plus or minus 2. Because what I'm doing is listing all possible factors. All the possible factors of P are 1, -1, 2, and -2. You're listing everything you used in those factor pairs. So now let's take a look at Q. Q is right here. That's Q. Q is positive 3. So what are the possible factors of positive 3? Well, 1 and 3, that's it. However, because it's positive, I can do positive 1 times positive 3, or I can do -1 times -3. So my possible factors for Q are plus or minus 1 and plus or minus 3. So now I'm ready to create my ratio. I found all the possible factors of the constant term and all the possible factors of the leading coefficient. So now let's put everything together. So let's take all the possibilities for the numerator. Well, for P, I could have plus or minus 1 on top or plus or minus 2 on top. So let's make all the pairs. And I'm going to make every single pair in this example just to show you the origin, and then I'm going to show you how to make it quick. So let's start off with positive 1. Positive 1 can be placed on top of anything for Q. We're going to take all of the green ones and put them over all of the blue ones. The example I use is if you have 5 t-shirts and 2 pairs of shorts, how many outfits can you make? Well, you have to take every t-shirt and put it with every pair of shorts. So t-shirt 1 goes with shorts 1 or shorts 2. That's 2 outfits. T-shirt 2 can also go with shorts 1 or shorts 2. That's 2 more outfits. So we're going to do the same thing here. So positive 1, I'm going to pair up with the bottom. So let me erase it. I'll do colors. Positive 1 can actually be a part of 4 different fractions. Okay. This is why my shortcut is going to make life easier for you. All right, so I can put that over anything on the bottom. Well, what's on the bottom for blue? There's a positive 1, there's a -1, there's a positive 3, and there's a -3. That's 4 possible answers from positive or -1, right? Now, that's for positive 1 only. What else could it be? -1. So guess what I have to do again? I have to create all those combinations again with -1. So I have positive 1 could be on the bottom, -1 could be on the bottom, positive 3 could be on the bottom, or -3. You see how much of a hassle that is? Well, now what am I going to do? I've done the positive and -1s. Now what do I have to do? The positive and -2s. So now I'm going to do positive 2, and you figured it out. There's going to be 4 fractions with positive 2. And then I'm going to have to do -2. And I'll put that one over here. -2, -2, -2, -2. And you can kind of see where this is going. So positive 2 can go over what's on the bottom? Positive 1, or it can go over -1. Or it can go over positive 3, or it can go over -3. And here, -2 also. Because I did positive 2, now I got to do -2. It can go over positive 1, or it can go over -1. It can go over positive 3, or it can go over -3. That means there are 16 different possible rational roots. However, if you look closely, you can see that some of them repeat. So let's look at the ones that repeat. So let's go first. What's 1 over 1? 1 over 1, and I'm going to put the factors here, is 1. Well, this one is also 1. -1 over -1 is also 1, so that's out. That we don't have to rewrite that one, okay? What's positive 1 over -1? -1. So -1 is an option, but guess what? That also gives me -1, so I don't need that one either. 1 over 3, that's 1/3. -1 over -3, that's also 1/3. I don't have to repeat it. So basically what you're going to see is you're going to get all of these. And you'll see there's going to be repeats. Now we got to do the same thing with the 2's. 2 over 1 is 2. -2 over -1 is also 2. -2, +1 over +2 over -1 is -2. And so is this one. Okay. Now we also have 2/3. We have +2/3 right here. This is also +2/3 because it's a negative over a negative. And the last one is going to be -2/3, which is the same as this one. Now that's a lot of work to get, how many do we have? 1, 2, 3, 4, 5, 6, 7, 8. That's a lot of work to get the 8 possible rational roots. And also writing them out like that is kind of tedious. So I'm going to show you on the next page how we can do this quickly. So here's my P and Q. I have +, -1, +, -2 on top, right, for my P values. And for my Q values on the bottom, I have +, -1, +, -3. Here's how you can save time for your factors. Basically, +, -1 is going to be on +, -1. Those are the 4 possible combinations with the 1's. Well, let's keep this simple. What's 1 divided by 1? It's 1. And I have every possible combination of positive or negative, so I'm going to either get a positive or a -1. If you look back here, do you see how I have that written right there? Instead of me writing 2 separate numbers, I'm just going to pair them up because it's positive or negative. Now we can do the same thing with the next one. So I have positive or -1. I also have to put that over positive or -3. So I did this one first. Now I'm doing this one. Well, it's going to be the same game. 1 divided by 3 is 1/3. And then I have every possible combination of positive and negative. So it's negative or positive 1/3. If you look on this side, that's when you have it written 2 separate factors. Then I'm going to go now to my second one. So let's go to the 2. Now I got to put the 2 on the 1. So I have positive or -2 divided by positive or -1. Once again, what's 2 divided by 1? 2. And then I have the positive and negative for both of those. If I go back to the previous one, there's my positive and -2. And then I have this pairing. So I have positive or -2 over positive or -3, which is positive or -2/3. Okay. So those are the 4 factors that I have for each one. Now you can write them like that. It's much quicker. So you have 4 possible answers. So the way you would write your factors are +or -1, +or -1/3, +or -2/3, and +or +or -1/3, +or -2/3, and then +or -2. And those are all your factors. An even quicker way to get it is take all these numbers and just stick a plus or minus in them based on how they're set up. So hopefully, again, the rational root theorem is not necessarily an easy theorem, but hopefully this gives you an idea of where everything comes from, how you get the roots just from your lead coefficient and from your constant. Now this function that we did here was a fifth degree function. It works for any function. So if I were to have, let's say my function was, and I'll use p of x to keep things consistent. It doesn't really matter whether we're doing p of x. I'll just use f of x. So if I have 5x squared minus 7x plus 6, I could have some more possible roots. What my p is going to be the constant, right? That's p. And the q is going to be 5 here. So what I'm going to do is I'm going to do the same thing. I'm going to factor them. What are all the possible, I'm going to do this the quick way now that I showed you the long way. What are the possible factors of positive 6? Well, positive 6, what are the factors of 6? This is the quick way. 1, 2, 3, and 6, right? Well, we always put positive and negative because even to get a positive number, you have a positive times a negative, and to get a negative number, you do, excuse me, for a positive number, you do positive, positive, or negative, negative, and for a negative number, you do negative, positive. So you're always going to have all the possibilities. For Q, I have 5. I have positive 5, so all of my factors for this one are just basically going to be 1 and 5. Plus or minus 1, plus or minus 5. So for all my factors, I have to put them on top of each other. All I have to do is just go, all my factors are going to be these guys, so plus or minus 1 over 1, which is just 1, plus or minus 2 over 1, which is just 2, plus or minus 3 over 1, which is just 3, and plus or minus 6 over 1, which is just 6. So that's my first round. Now I have to pair up the rest of them. So I also am going to have plus or minus 1 over 5, plus or minus 2 over 5, plus or minus 3 over 5, and plus or minus 6 over 5. So you actually have all of these possibilities. Again, just because it's a possibility, these are all possible. It does not mean that they are actual. You don't know if they're actual. They're possible, not actual. So you would have to test to see how they work. Anyway, hopefully that helps you with rational roots.